Hello, my name is Ahmed Kamaluddin from the Chair of Adaptive Dynamic Systems, Technische Universität Dresden, Germany. Today I would like to present my paper, a Hybrid Memory Accelerator Tile Architecture for FPGA-based RISC-V Manycore systems. Tile-based architecture increases the flexibility and scalability of heterogeneous Manycore systems compared to the traditional multi-core architecture. Although custom hardware accelerators could be inserted in a tile-based architecture, and it requires a large size of private local memory per tile. Therefore, to reduce the many-core system memory footprint, we can share the memory between the accelerators and the general-purpose tile. Our main contributions in this paper is to provide a hybrid memory accelerator tile architecture that can be reused for two modes of operation, as a scratchpad shared memory between the compute tile or a shared custom hardware accelerator. The hypertile architecture supports a non-coherent memory that can be shared between the compute tile, and also it provides the flexibility to change the hardware accelerator functionality at runtime through Xilinx dynamic partial reconfiguration technique. The hypertile architecture can be seamlessly integrated to a tile-based architecture through the network on a chip. Two separate network on a chip interfaces are provided for data and control signals. It supports the flexibility to change the size of on-chip memory. The hypertile consists of a data path and control unit. Hypertile data path is responsible to establish data path between the network interface for Rx and Tx to the on-chip memory. There are three types of data paths that can be established: memory read, memory write, and hardware accelerator. For memory read and write data paths, they can be established in parallel, therefore we can support a dual memory access. The hardware logic can be changed at runtime through dynamic partial reconfiguration. The hypertile control unit handles all memory and accelerator requests through control messages. Control messages are sent and received through the network on a chip between the RISC-V-based compute tiles and the hybrid memory accelerator tiles. The control messages carry the control signals that are used to configure the hypertile data path based on mode of configurations. The control unit has a finite state machine that's implemented to issue control signals to the tile data path based on the received control messages. A message-based protocol is developed for interaction between RISC-V compute tiles and hypertiles. There are two types of messages supported here: data and control messages. The control messages contain the control packets that carry the configuration signals from the RISC-V tile to the hypertiles. And the data message contains the data packet that includes the read and write data from or to the hypertiles based on the data path configuration. Data and control messages consist of several packets, and each packet contains 33 flats. In order to evaluate the hybrid memory accelerator tile architecture, we integrated it into a tile-based many-core architecture. The tile-based many-core architecture consists of several compute tiles, and each compute tile contains 4 RISC-V cores based on the RV32 IMC instruction set architecture. Each compute tile has a non-coherent shared memory for all RISC-V cores, and the compute tiles are connected to the network on a chip through a memory map network interfaces. In this paper, two many-core configurations are supported for 4 and 8 compute tiles. In order to evaluate the memory bandwidth of the proposed hybrid memory accelerator tile, memory copy functions are executed on RISC-V compute tiles to copy a block of data from or to the compute tile local memory to from the hypertile on a chip memory. Therefore, for memory read mode, a maximum memory bandwidth of 100 MB per second is achieved. On the other hand, for memory write mode, a maximum memory bandwidth of 400 MB per second is achieved. Therefore, the total memory bandwidth is 500 MB per second, as we support here a dual memory access, so we can have read and write simultaneously. Several signal processing kernels are used for evaluation, like FFT, 3D convolution, 2D convolution, matrix-matrix multiplication. These signal processing kernels are parallelized on RISC-V based compute tiles. In this paper, we support two mini-core configurations. The first mini-core configuration consists of 4 RISC-V compute tiles and 1 hypermemory tile, while the second configuration consists of 8 RISC-V compute tiles and 2 hypermemory tiles. According to the shown image, we can see that the total memory bandwidth using 2 hypermemory tiles on the second mini-core configuration can achieve double the memory bandwidth that we can get from 1 hypermemory tile on the first configuration. Several hardware accelerator IPs are selected to be used inside the hypertile, like 3D convolution, Gaussian filter, and Xilinx FFT. All hardware accelerators support access stream interface, compatible with hypertile interface to integrate hardware accelerator logic. The accelerator memory units are tightly coupled with the accelerator logic, which reduce the data transfer between the PRAM and the accelerator logic. Finally, a reconfiguration time of 75 milliseconds is achieved through the JTAG interface to change the accelerator logic at runtime. To conclude this paper, a hyper-memory accelerator tile architecture for FPGA-based RISC-V mini-core system is proposed. The proposed tile features modular and reusable architectures that can be seamlessly integrated in a NOC-based system. A message-based controlling protocol is used for communication and interaction between RISC-V-based tiles and hypertiles. A maximum memory bandwidth of 500 MB per second can be achieved per single hypertile. Thank you for listening.